Hello, this is Ms. Nichols, and this lecture video is on the parts of the circuit and circuit diagrams. The essential question for this video is, what are the critical parts of a circuit and how do you represent them in a drawing? So there are four components in every circuit. Number one, every electrical circuit needs to have an energy source. Number two, every circuit should have a resistor, sometimes called a load, and that is essentially the thing that, the point of the circuit, the thing that takes the energy from the energy source and turns it into something useful. The third thing every circuit probably will have is some kind of conducting wire that is connecting those items to each other. And then most circuits will have a switch that we use to turn the circuit on or off. So now I'm going to go through a few details about each of these components and show how to recognize them in drawings. The first is the energy source. This is, again, the object that is going to be giving or storing the electrical energy in the electrons for my circuit. Some examples of energy sources are batteries. That's probably the most common one we're going to be using, sometimes called a cell. Capacitors that we learned about in the last unit can be energy sources. Wall outlet, of course, solar panels, generators, etc. So these are some pictures of the actual physical devices. In a drawing of a circuit, sometimes called a circuit diagram, however, these different energy sources will have a very specific way of drawing them. That figure shown in the bottom left there is how you draw a battery in a circuit. It's basically two parallel lines, one of which is longer than the other one. The longer one is the positive side of the battery. Sometimes it's labeled positive and sometimes it's not. And then the two lines going off are the wires, which we'll talk about in a little bit. Capacitors are drawn similarly to batteries, except for they have two equal length parallel lines instead of being different lengths, and they're not usually labeled positive or negative because it depends on how they're charged up. So that is how you would draw those two components in a circuit diagram. So as I mentioned, the resistor or load is the element that is transforming electrical energy into other kinds of energies. There are lots of examples if you look around you. Anything plugged into a wall is an example of a resistor. So a light bulb, a toaster, an electric motor, a buzzer of some kind. There's also plain old resistors, I'm calling them, and that's basically a circuit component that is designed to just take electrical energy and waste it. We'll talk about why you'd want to do that a little bit later on, but maybe you've seen those things inside circuit boards or just around the world before. When you are drawing resistors in a circuit diagram, the most basic way of drawing them is shown below that plain old resistor. It's just a series of up and down zigzags to represent a resistor. And that's certainly how you would draw a regular resistor. You can also use that same symbol to represent a light bulb or a toaster or anything else, although there are also some specialized symbols for those other types of resistors that will occasionally pop up. For example, those two symbols also can represent specifically light bulbs. So if you see those in circuit diagrams, they are resistors, but they are also specifically light bulbs. Obviously, every circuit diagram is going to contain wire. We have to have something conductive that is going to make a complete circuit from the energy source to the resistor and then back again to the energy source. One note in general, the length of the wire is not relevant in this class, or at least when we're dealing with what's called an ideal wire. We remember doing ideal gases, and so unless we are given otherwise information about the wire, we assume that it doesn't matter how long it is. Some examples of wires in circuit, well, wire. But anything conductive can act as a wire. So a human could be a wire if you are unlucky, or anything that electricity can go through, like water, would be an example of a wire as well. In a circuit diagram, wires are just drawn as a line that is going to connect all the components with the power source. Most circuits will have a switch or a button because otherwise you can't ever turn them on or off. And we say those switches and buttons have two states. Open is actually the same as off. Okay, so if a switch or button is open, then it prevents electricity from flowing through the wire and it would be disconnected. If the switch or button is closed, that means that there is a conductive pathway from one end to the other, and the switch would allow electricity to flow through. So you can use switches and buttons to complete circuits or to turn certain resistors on and off. Some examples from your life: obviously, anytime you have a light switch or a power button on something. Circuit breakers in your house are examples of switches as well. In a circuit diagram, a switch is usually drawn sort of like a little door, and open looks like an open door, and you can see that the wire is essentially broken. Okay, so let's look at some put together circuit diagrams. You know, if you actually wired up a light bulb like this, you could draw a picture of this circuit in a physics way, which would be known as a circuit diagram that includes the symbols for those components instead of the components themselves. So that circuit diagram would be similar to the one shown below, although there's not a switch in the picture, but most light bulbs will have switches on them. So we've got our battery shown, positive and negative. That thing on the right is the light bulb, and then the wire is shown below. You'll notice that the circuit diagram is much tidier and more organized than the actual light bulb itself. And if you ever do any wiring in your house, which I would strongly encourage, you'll notice that this is true. Drawing the schematic or the circuit diagram is the easy part, but dealing with all the crazy curvy wires that are going through all the walls is a little bit more challenging. But these two things are functionally the same thing. We use circuit diagrams to sort of visualize in an easier way what's happening. So this might be what the actual wiring in your house looks like, and maybe you have a circuit diagram that's much cleaner. Those two don't actually match each other, but the point stands. The last thing I want to talk about in this video is what's really happening in a circuit, sort of from an atomic level. We know that atoms all have electrons. The electrons are not created by the battery. That's not what's happening with electricity. The electrons are already there. We can't create or destroy them, or we'd violate all those conservation principles in physics. So if you could picture a circuit here below, all those little electrons start off in the circuit from the very beginning, and we're not going to gain or lose any of those electrons, or gain or lose any charge, because both of those things are conserved properties. So the power source, what it does is it energizes the electrons by essentially pumping them in one direction. And you can see this in the simulation where the electrons on the negative side of the battery have been pushed closer to each other. Remember from our electrostatics unit that forcing two like charges together is a way of storing energy in those charges. And so that battery is basically taking its chemical energy and using it to turn it into electrical potential energy by shoving those electrons close to each other. Now, each of those electrons on that negative side is going to have a higher amount of electrical potential energy per electron, which is otherwise known as voltage, right? Energy per electron is voltage. Batteries all have characteristic voltage values that's based on the chemical reactions inside of them. If you grab any old battery, you'll see it says on that battery how much voltage that battery is. That basically tells you how much energy is it able to force those electrons to have by its kind of chemical reaction that's pumping them from one side to the other. So we've got all these energized electrons that are close to each other. When that switch is closed, then those packed up electrons all of a sudden have a complete conductive path to get back to the other side of the battery where there is an excess of protons left over. So that's what happens when the switch closes, is all of a sudden there's like a little road that allows those electrons to get from the place where they don't really want to be all piled up to the other side of the battery where they've got a lot more space and excess protons. In the process of moving from one side of the battery to the other, the energy has to go somewhere. It has to transform into something. Some of that energy is going to be kinetic energy, right? The movement of the electrons, but because that would actually turn into heat, kinetic energy at a molecular level, the resistor's function is actually to take that kinetic energy, or to take that electrical potential energy and turn it into something else other than heat, so it doesn't just waste it. So the resistors will take some of that energy those electrons have and they transform it into other kinds. That means that the electron spacing sort of changes most dramatically when the electrons are passing through the resistor, and the voltage of each electron is changing at the resistor as well. We might define this as a negative delta V, right? Positive delta V when it gained energy at the battery, and then negative delta V when it loses that energy again as it goes into the resistor. A note about this, and we'll come back to this later, but it is sort of a law of physics, it's a law of conservation of energy, that electrons have to use up all of their electrical energy before they return to the battery, and then they kind of start the cycle again. In other words, the delta V for the entire circuit is 0. Whatever energy they gain at the battery, they're going to lose at the resistor or in the wire as they move through that battery, or through that circuit. Okay, we've reached the end of the video. Please take a minute to revisit the essential question, which is what are the critical parts of a circuit and how do I represent them in a drawing? Thanks for watching.